You hear about averages all the time, right? The average salary, average rent, average time you spend staring at your phone. It seems so simple. But what if I told you that just looking at the average can be, well, totally misleading? Today, we're going to look beyond that one single number to find the real story hiding inside the data.
Okay, let's just jump right in with a question. Imagine you're packing your bags for a trip. You've got two choices, City A and City B. You check the weather and look at that. They both have the exact same average daily high temperature, 15 degrees Celsius. Easy, right? You'd probably pack the same stuff for either city. Or would you?
So what's really going on under the hood of that 15-degree average? Well, in City A, the weather is super consistent, predictable, a light jacket, and you're good to go. But City B? Whoa, that's a completely different story. You'd need a winter coat one day and shorts the next. Same average, but a totally different reality. And that spread, that difference in the data, that's what statisticians call variation, and it is absolutely key to understanding the whole story. Okay, so if the average isn't enough, how do we actually measure this kind of wild spread in the numbers? Well, our first stop is going to be the simplest tool we have, the range.
It's called the range, and it's pretty much exactly what it sounds like. It's a super simple calculation that only looks at the two most extreme points in your data, the absolute highest value and the absolute lowest value. It's a really quick and easy way to get a first glance at how spread out everything is.
Let's try it out on our crazy weather in City B. The calculation couldn't be easier. Step 1, find the highest temperature. That was a warm 35 degrees. Step 2, find the lowest. That was a freezing -5. And step 3, you just subtract the lowest number from the highest number. And there you have it, a 40-degree range. That number instantly tells you the weather in City B is all over the map. For comparison, City A would have a tiny little range of just 4 degrees. So yeah, simple and pretty effective, but only up to a point. And here's the catch. The range has a big blind spot. It completely ignores every single piece of data in the middle. It only cares about the two most extreme values, which, could just be weird outliers. We need something better, something more robust that tells us how all the data points are behaving.
So this leads us to a much, much better idea. Instead of only looking at the edges, what if we measured how far, on average, each and every data point is from the middle?
This brings us to something called mean deviation. Now, the idea here is a huge step up. Instead of just the two extremes, we look at every single temperature. We figure out how far each one is from that average of 15, and then we take the average of all those distances. See? Now, every single data point gets to have its say in describing the spread. But in the world of statistics, there is one measurement of spread that is king. It's the most common, the most powerful, and really the most respected tool for this job. So let's talk about standard deviation. Now, the official definition says standard deviation is the square root of something called the variance. I know, that might sound a bit technical, but the idea behind it is actually beautiful. It gives us one single number that tells us the typical distance any given data point is from the average. Now, you might see a formula that looks like this, and yeah, your eyes might start to glaze over. I totally get it. It looks intimidating. But forget the symbols for a minute. What this formula is actually doing is pretty intuitive once you break it down. So let's just walk through it. First, just like we did before, it finds the distance of each point from the average. But then it does this clever little math trick. It squares all of those distances. This does two important things. It makes every number positive, and it gives a little more weight to the points that are really far out. Then, it finds the average of all those squared distances. And finally, for the last step, it takes the square root, which basically just undoes the squaring part, and brings the number back to a scale that makes sense to us. So, if you remember one thing, let it be this. When you hear standard deviation, just think the typical distance from the center. That's it. A small standard deviation means all your data points are huddled together real close to the average. A large one means they're spread far and wide. And this just explains our city example perfectly. City A, with its super consistent weather, would have a really low standard deviation. Its temperatures just don't wander far from the average. City B, on the other hand, with its wild temperature swings, is going to have a really high standard deviation. Just one look at this chart tells you which city is predictable and which one is just pure chaos. Okay, so we have this powerful new tool. What's the point? What can we actually do with it? Well, this is where it gets really cool, because it lets us compare the consistency of things that are completely different from each other. For example, think about this question for a sec.
What's more consistent? A student's test scores that might go from, say, 80 to 95, or a professional golfer's drives that might range from 290 to 310 yards? I mean, how on earth can you compare test scores in points to driving distances in yards?
The answer is an amazing little tool called the coefficient of variation, or CV. It's such a clever idea. What it does is it takes the standard deviation we just learned about and it turns it into a simple percentage of the average. By doing that, by turning the spread into a relative percentage, it just gets rid of the original units. So suddenly, it doesn't matter if you're talking about points or yards or miles per hour. We can finally make a true apples-to-apples comparison of how consistent things are.
And the rule is so simple. The lower the CV, the more consistent the data. So if that student's test scores have a CV of 5% and the golfer's drives have a CV of 10%, we know for a fact that the student is relatively more consistent, even though we were comparing test scores to yards. It's an incredibly powerful way to compare performance and precision in totally different fields.
So let's just wrap up what we've figured out here. We started off realizing that an average only tells you where the center of the story is. To get the whole picture, you have to measure the spread. We started with a simple range, but we saw it had some big flaws. Then we leveled up to the powerful standard deviation, which gives us that typical distance from the center. And finally, we used the really clever coefficient of variation to compare the consistency of pretty much anything we want.
But of course, there's always more to the story, isn't there? We've been assuming that our data is spread out pretty evenly on both sides of the average. But what happens when it's all bunched up on one side? Well, that gets into a whole new concept called skewness. But you know what? That's a story for another day.
So the next time you see an average number thrown at you, you'll know that's just the beginning. The real insight, the real story comes from asking the next question. Yeah, but how spread out is the data? The average tells you where you are, but the variation tells you the whole story of the landscape around you. So what question will you ask to see the full picture?